we have learned that given some f, which is compactly supported, C infinity from the complex numbers, we have a couple of nice identities. At this point, we know that if we take the Cauchy transform, of the anticonformal part of the gradient, we end up with the function back itself. We know that if we take just the ordinary part of the gradient, let me start everything again. So we know that if we take the anticonformal part of the gradient and take the Cauchy transform, we end up with the function back itself. If we take the conformal part of the Cauchy transform, or we take the derivative, the conformal derivative of the Cauchy transform, that ends up giving us the Beurling transform, and the Beurling transform is defined via this singular integral. Let's just write it again since it's our key topic of the day. Minus 1 over pi, the limit epsilon goes to 0. So the Beurling transform of f is this function which at z is given by this. It's the limit as epsilon goes to 0 of the complex plane, take away the ball of radius epsilon around z, of f of zeta minus z squared d zeta, like this. Okay, and then we've learned that this limit makes sense because we've showed this. We also know that all the derivatives can be passed through all of these operators, right? Let me just say this. D by dz of f equals c of df by dz, d by dz bar of c of f is c of dz bar, and the same for s as well, and same for s. That's where we left things, huh? That stuff we know. Okay, so now we're going to dig deeper into the properties of the Beurling transform that we'll need. So, first thing is that the Beurling transform takes the anticonformal part of the gradient and maps it to the conformal part of the gradient if we have some mapping of compact support as a consequence of these identities. So, claim. Let's do it this way. And why so? Let's look at what we know from these identities here. We know that the conformal derivative applied to the Cauchy transform gives us this guy here, the Beurling transform. So let's write that. So that is the same as saying d by dz. Let's do this one step at a time. F of df by dz bar by this identity up here, that's the same as d by dz of c of df by dz bar, right? Just using this identity here. Okay, and now we are going to think about this as the Cauchy transform acting on the conformal part of the gradient first, and by this identity just gives us back the mapping itself, so then this is all we have. So it's just one line, okay? So just from star, and from this guy, star, star, that's what we have. Yeah, so formally it's very simple. Yeah. Another claim. If we take any mapping of compact support and it's just infinity, then the following is true. If we take the integral of the norm of the conformal part of the gradient squared dz, that's the same as the integral, not over the domain, it's over the entire complex plane. Like this. Let's do the double integral because I've been doing that to just differentiate between curves and solid integrals. Then this is the same as this, the anticonformal part of the gradient squared dz. Okay, proof. So we're going to use some of the identities we talked about right at the beginning when we decompose things into anticonformal and conformal parts of gradients. So recall, and maybe I'll just show this to convince you guys of this. Recall, if we take matrix A belonging to 2 by 2, then I claim that the determinant of A was the same as 1 over 2, the Hilbert-Smith norm of the conformal part of gradient squared minus the anticonformal. So after this, I'll just write this out and show this to you. Okay. And we're going to use this fact because, as we know, this is the anticonformal part of the gradient when we think about f as a mapping from R2 to R2, and this is a conformal part, right? And the key thing we're going to use here is that determinants of derivatives can be written as a divergence, which is a very useful fact, which we're probably going to use later anyway. So neat identity. So given, stick with capitals. Given some h, which is everything smooth, from something in R2 into R2, then the determinant of the gradient of h, which is now a 2 by 2 matrix, of course. What is this? This is h1, 1, h2, 2, minus h1, 2, h2, 1. And it turns out that this is the divergence of h1, h2, 2, minus h1, h2, 1. Because if we just apply the divergence of this expression, divergence, let's just call this thing star, 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 divergence of star, 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 is what? So we apply the divergence first to the h1 and then to the h2, 2. So let's say that again. I'm going to apply the first partial to the first coordinate, first to the h1 and then to the h2, 2. So then that's going to give us h1, 1, h2, 2, and then plus h1. Now applying it to this guy, h2, 1, 2. Yeah? Now we apply the second partial to the second coordinate, first going to hit the h1. So we're going to have h1, 2, and then h2, 1, and then we're going to apply the second partial to this expression. We're going to have minus h1, h2, 1, 2, and we have that these guys cancel like this, and that's, yep. You cannot see the last line. So we get the cancellations of these terms, and we get exactly this identity that we want. Yeah? So determinants can be written as a divergence. This is an extremely useful thing, and I think I'm going to use it later when we talk more about weak convergence. But it's useful for us right now because of what? Because we have this identity with this identity. So tell me how we're going to use them. How we're going to use them together to show the claim. Well, I mean, since we want this, right? Yeah, and since we have this identity, let's turn F into a mapping from R2 to R2, right? So let's do the standard thing. Good, yeah. So we're just going to put all these pieces together just to see summarized. So let's take, or let, carefully clean off something and then make a mess. So let F tilde be the standard real version of the R2 to R2 version of this complex function, or where f of x comma y is equal to f1 of x comma y, f2 of x comma y, where f we think of as f1 plus I times f2. Yeah. So this is the guy we've done a lot. We've gone from complex functions to functions from R2 to R2. Then what do we know? Then we know that the determinant of the gradient of f tilde, like this, by this identity here, is a half times the determinant of f tilde conformal minus a half norm squared minus norm squared of this thing, anticonformal squared like this. This is exactly the same as the norm of the conformal part of the gradient. So this half here takes into account the fact that we have this 2 by 2, so it's the right constant in front. So then this is exactly this thing minus this thing. Bar. Try that again, the bar higher. Z bar, like this. Yeah. And we also know that this can be written as a divergence. Yeah. And the integral of determinant of the f tilde is the double integral dx dy, like this, is the integral of the divergence of this particular vector field I gave you, dx dy. And someone else tell me why we know that this divergence is 0. Right, the function's compactly supported, yeah? So whatever large boundary we decide to take this around, then it's just vanishing, so then this is 0. Cool. So this exactly says that the integral of this thing, which is the integral of this thing, is 0, and that's exactly our claim. Yeah? That's exactly our claim. Everybody with me? Yeah? Cool. I will erase the board. Now the next thing we're going to show is that this guy, this operator this operator S, the Beurling transform, is actually going to be preserving the L2 norm. It's going to be an isometry. Is that the right word? Don't think it's the right word. Maybe it is the right word. Anyway, it's going to be preserving the L2 norm of the gradient. So if we take the Beurling transform of a function which is C infinity compact support, then the integral of the L2 norm of the Beurling transform will be the same as the integral of the Beurling transform squared will be the same as the integral of the function squared. That's what we're going to claim. And what this identity and what this fact we have just shown is that that's true for the special case of functions which are given by the anticonformal part of the gradient. Yeah? And our claim is going to be true for all functions. So while I erase the board, think about the issues involved in showing that. Okay, maybe before I do that, I'll show you the linear algebra lemma that I implicitly, well, that I used in that. So lemma, it is indeed the case that the determinant of A is equal to 1 over 2, this thing squared minus 1 over 2, this thing squared. Let's quickly just verify that. So, proof. So how does this decomposition go? So A is equal to A11, A12, A21, A22, and therefore AC is A11 plus A12, A12 minus A21, minus A12 minus A21, and then A11 plus A22. That's what this guy is. Anticonformal, brackets. Is 1 over 2, A11 minus A22, A12 plus A21, A12 plus A21, and then minus A11 minus A22. Right? We agree that this is anticonformal, and if we add these guys together, we get back the original guy. Yeah? This is the coordinate-wise the correct representation. Yeah? So if we take these things and square them, let's take the Hilbert split norm, then we're going to have that AC squared is what? It's going to be this thing squared plus this thing squared plus this thing squared plus this thing squared over 4. Right? So 1 over 4, but then so we have this thing squared plus this thing squared. There'll be just 2 of them, so let's put it over 2. So 1 over 2 of A11 plus A12 squared plus A12 minus A21 squared, like this. Yeah? And in the same way, and it's going to be this thing squared plus this thing squared plus this thing squared plus this thing squared, but then that reduces down to A11 minus A22 squared plus A12 plus A21 squared, like this. So if we take half of this guy minus a half of this guy, what should be clear from this expressions is that all the A11 squared, the A12 squared, the oops, this should not be this, should be 2. So the A11 squared, the A22 squared, the A12 squared, the A21 squared will be cancelled by these guys here. Yeah, just algebraically we can see that. Yeah, the only thing that will survive when we take this guy minus this guy will be the mixed terms when this is multiplied by this, and this is multiplied by this, and this is multiplied by this. Everything else will just be cancelled because the signs are the same, yeah? Cool. So, let's just use actually a form, let's call this thing star. So, star is going to be, let's pull out the half, and we are also going to get the half from this thing, so it's going to be a quarter. And then just the mixed terms. So the mixed terms here will be 2 times A11, A22. The mixed terms here will be minus 2 times A12, A21. Yeah? that's from this thing, let's put a bracket around this, and then minus the mixed terms here. So the mixed terms will be minus A11, A22, but there's two of them, so it's, is that right? Yeah, so it's minus 2A11, A22, yeah? And then the mixed terms here will be 2 times A12 times A21. Yeah, like this. All right, and that seems to work, right? Because this will give us 1 over 4 of 4 A11, A22, and then minus 4 A12, A21, which is exactly the determinant of A. So we are happy. Yeah? Cool. So we do indeed believe the linear algebra lemma that we used in the last identity. Okay, cool. So claim that we actually have that the L2 norm of f of any function g is equal to the L2 norm of g for any g belonging to compactly supported C-infinity functions, complex numbers to the complex numbers. Okay. Proof. So, since we know that if we take the anti-conformal part of the gradient, the Beurling transform transforms that into the conformal part of the gradient. And since we know that the L2 norms of both of those guys are the same, I think I'm going to have to develop a more efficient notation for these things. L2. That's what we just learned in the previous on the previous board, right? So putting these things together, so true for all G which happen to be the anticonformal part for some f which is compactly supported from the complex numbers to the complex numbers. Yeah? So it's true for this particular class of functions which are the conformal part of the gradient of some compactly supported C-infinity function. Yeah? Okay, so let L be this set of functions, the set of functions that are like this, set of G from, so I write this the long way around rather than just writing conformal part of the gradients. G is equal to like this. F. Yeah? Let's let L be this thing. So this thing has got obvious nice structure, right? If we add any two functions, they're still inside this space. If we linear multiply such a function, it's still inside this space, right? So it's actually a subspace. Yeah? This is a subspace. So let's consider the space that is orthogonal to this subspace inside the space of compactly supported C-infinity functions, the complex numbers. But let's talk about what inner products are when we have functions with the complex numbers to complex numbers. So the complex inner product which we're going to write like this. H comma W is, so we're going to write the double integral just to emphasize we're in the complex numbers, and it's going to be H times W complex conjugate, like this. dz. Okay, which might seem a little bit surprising for you guys, but one of the things we basically need for one of the basic things we need for the inner product is that when we inner product a function with itself, we want to have the norm of the function squared. Yeah, and if we do the complex conjugate like this, then sure enough, that's true, right? And if we didn't have the complex conjugate, we'd have h squared, which wouldn't be the norm of the function squared. So this is the L2 norm squared of the function like this. Yeah? So this is the reasonable definition, but no, it's not symmetric. If we flip this around, then we need to put a complex conjugate on top of the entire thing, right? So it's not a symmetric expression. But it is an inner product. It is serving a product, serving the purpose of an inner product for us. So if we want to consider the set of functions that are orthogonal to L, then L perp is the set of H, well, set of functions that are inside this space of C infinity functions, such that slightly matters which way around I do this. It doesn't matter too much. H of G equals 0 for all G belonging to L. Right? This is the orthogonal complement of the subspace. Yeah. And what we're going to do to show this is to show that this space is actually nothing. It's 0. It just contains the zero function. Okay. And if we do this, that means the entire space of C infinity functions is inside the space L. In other words, we can realize every single function as the conformal part of a gradient. You know, which is kind of a surprising result, but nevertheless, it's true. Okay, claim that L perp is just consisting of the 0 function. Okay, proof. So, given f belonging to L perp, what does that mean? Let's first do f is u plus iv in the standard way. And what does that mean? That means that f times something which we get from a anticonformal the gradient, this thing is equal to 0 for any g which is compactly supported C infinity. Complex numbers to complex numbers. Yeah. This is our claim. Yeah. Now we are going to use this in the following way. So let us write out in coordinates what we have here. So what is this guy? This guy is a half of d by dx plus I times d by dy, right? And we're going to let g be g1 plus I times g2. Yeah, so writing out in coordinates, d by g is equal to a half. And then let's put the partial on this, so it's g1 comma x plus I g2 comma x, like this. And then I times g1 comma y plus I g2 comma y. Right? And then let's put the real and imaginary parts together. So the real will be this guy, and then I times this guy, right? So it's going to be a half g1 comma x minus g2 comma y. And then the imaginary part will be this guy, g2 comma x, like this. And then this guy, that's g1 comma y. that's what we have. Yeah. So then from star, what is that saying? That's saying that we have this double integral of u plus iv, and then the complex conjugate of this thing, the half, we don't care about it. Let's just take it out from this. So the complex conjugate is this thing. It's g1 comma x minus g2 comma y, like this, plus I g2 comma x g1 comma y, like this. And sometimes I write dz, so let's continue to write dz. Well, actually now we're doing things in coordinates x and y, so let's write dx dy. Because when we write this thing, when all the double integrals we do, dz, that means integrating with respect to the x and y standard Lebesgue measure, right? That's what it means, yeah? Minus, right? So this thing is defined to be equal to blah, blah, dx dy. Okay, so let us look at this thing. So this thing is equal to 0, and let's put the partials on the other sides, right? So I can integrate by parts and put the x onto this thing and the y onto this thing, yeah? And the same for this, yeah, that's what I want to do. Okay, so let's do it. So this is equivalent to double integral. We're going to have ux plus ivx, putting the x on the other side. So I'm going to forget about the minus sign because everything's equal to 0. And then when I put the y on the other side, but now this will become minus times g1. And then we're going to have minus u of y plus I v of y. And now g2, like this, putting that thing on the other side. Minus I. And now we've got this character here, this guy here. We're going to put the x on the u, so u of x, v of x. Put this around everything. And then we put the y on everything, and then the sign remains positive in this case, so plus u of y, v of y, like this. Forgot to multiply by the function. So when we put the x on everything, then we're going to have this g2 like this. And when we put the y on everything, we're going to have u of y plus I v of y, and then g2 like this, right? dx dy equals 0. There is no z1. Do you mean g1? Yes, g1. Yes. Thank you. Perfect. Okay, so let's look at what this gives us. This says that for any real function, or any function g whose coordinates are g1 and g2, like this, they're C infinity. That's the only thing we care about. That's the only property that they have. We have this expression here. So if we put everything that we know about g1, or if we put things in terms of the testing against g1, we have this tested against g1, and this tested against g1, and that is good because what is that? So Then we have u of x plus I v of x. And let's multiply this complex number through. And we're going to have, let's put the minus, and we'd have u of, or I u of y. And then we're multiplying complex numbers, we're going to have minus v of y. Like this, all of that stuff is tested with respect to G1. Yeah? And let's put the stuff which tested against G2 together. So we are going to have minus uy plus I vy times G2. And then no, let's put this always, G2 is on the outside. Let's take the complex number through. So then minus u of xi minus v of x, like this, G2. All of that stuff, dx dy, is equal to 0. Yeah? Cool. All right, so G1 and G2 are independent. They are any functions that we like, right? Any smooth functions that we like. And u and v are also smooth functions. Yeah? So if we just take G2 to be equal to 0 for a second and just read off what we have here, then we have this thing we have here. So let's put together the real and imaginary parts. So then the real part is this minus this, so u of x plus v of y, and then the imaginary part of this, so v of x minus u of y, like this, times G1. And putting the real and imaginary parts of this thing together. So the real part is v of x minus u of y, and then I of, well, both of them are minus. Let's put minus here. Minus u of x plus v of y. Like this, right? dx dy. Okay. And again, G1, G2 are completely independent functions, just C infinity functions. So if we take G2 to be equal to 0 and we just look at this thing, right, what will this imply? This implies that if this is true for every possible real valued function G1, yeah, then this complex valued function, when we integrate it over the entire complex plane, it's 0 for every possible real valued function. Yeah. That's only possible if this is identical to 0 and this is identically equal to 0. Yeah? Because if that wasn't true, then we should be able to, well, we can find some function G1 such that the integral is non-zero. Yeah? If this entire thing here was any non-zero complex number anywhere, right, we would just take some G, which has got a little, which is compactly supported in that tiny neighborhood where this thing is almost constant, equal to that non-zero value. Yeah, just a little bump function, and we get a contradiction. You guys see what I mean? So if there is a point where this entire complex number was not equal to 0, then we take a little neighborhood where it's almost constant, where it's within some tiny epsilon of that non-zero complex number, right? So, and that epsilon is much smaller than the complex number. And then we take a function of compact support, just support it inside here and test it against it. Yeah? So our function will be something whose support just goes up and down like this. But obviously, it's from R2 to R, so it's a bump that lifts off like this. Then integrating this against this, since this function is almost constant inside this neighborhood, there's no any cancellations going to happen, and we get a contradiction. All right, cool. So since this is true for any function g, g1, g2, then this implies that u of x is equal to minus v of y, and v of x equals u of y from this. Now let's look at this side. So now let's take g1 to be equal to 0. Let's just mess around with g2, and exactly the same thing is true. The only way this can possibly be 0 for every choice of G2, where G1 is 0, is if this complex number here is entirely equal to 0 everywhere. Yeah? So this thing implies that v of x equals u of y, which is the same thing we had before, and then u of x equals minus v of y, like this. Yeah? Yeah, which is the same equation, same two equations. Yeah. These guys look a little bit familiar, right? They look a bit familiar, but they're not exactly familiar. Right? What do these things look like? What do these things look like? They're not exactly Cauchy-Riemann equations, right? So the Cauchy-Riemann equations are equivalent to being inside the conformal matrices. These are the anti-conformal matrix. This is an anti-conformal matrix, this identity. So it's not exactly the same thing, but it's a very similar thing. In particular, the nice things that we knew about satisfying the Cauchy-Riemann equations are still going to be true for these equations, specifically that u and v are going to be harmonic, right? Because look, u and v are both C infinity. We can differentiate them as much as we like. So if we do u of xx, that's the same as minus v of xy, like this. And u of yy is equal to v of xy from this thing. So u of xx plus u of yy is just equal to 0. And the same game for v. So v of xx equals u of xy, and then v of xy from this thing is minus v of yy is minus u of xy. So then we add them together, v of xx plus v of yy equals 0. Yeah? So u and v are harmonic. All right, how does that help us? Liouville's theorem applies for holomorphic functions, right? And this doesn't quite form a holomorphic function. We can turn it into one with making a simple transformation. So basically you're correct, but we can't so instantaneously apply Liouville's. But actually, I mean, that's almost as good as that's almost as simple as what I was about to say. So yeah, after flipping things around, so we'll have to make a change. We'd have to define, say, w to be equal to u minus I of v. Then if we did this, then w would satisfy the Cauchy-Riemann equations, and then we could apply Liouville's theorem exactly as you say. Yeah. So we could apply Liouville's theorem, or we could think about what we know about harmonic functions. So u and v are harmonic. What else do they satisfy? They have compact support, right? They have compact support because f has got compact support. Yeah. So can we have a harmonic function of an entire R2 which has got compact support? The answer would be no. But why no? What do we know about harmonic functions that prevent that being true? Maximum principle, and another more elementary thing. What's the first thing about harmonic function? Mean value theorem, right? So if we had u and v, which are compactly supported, suppose the support is like this, we just take a ball whose radius is bigger than this for any point inside the plane. By the mean value theorem, the value of u is equal to the average around the outside of the ball, but there's no support on the outside of the ball, so u and v have to equal to 0, right? So by mean value theorem, so the maximum principle just follows the mean value theorem. We have that u and v equals 0 everywhere because compact support. Yeah, cool. So this implies that whenever we have a function where if we test it against every function g, which is smooth, compactly supported, and if a function f, compact support, which is smooth, we test against such a g, we test it against the anticonformal part of the gradient, then this calculation implies that actually f is identically equal to 0, which gives the claim. Okay, so there is no thing inside the orthogonal complement of L. L is an entire space, right? So let's finish with this. So L is equal to all of these guys, C infinity functions from complex support to complex support, yeah? And therefore, when we apply the Beurling transform to any function f, then f can be represented as the anticonformal part of the gradient, and so this identity, as we just talked about, will be true, where this is the L2 norm over the complex numbers. Yeah? Okay, so there's a linear transformation that preserves distances between these two Banach spaces when we consider functions of compact support. Yeah? Cool. Now I claim that this is going to allow us to define the Beurling transform on any L2 function. Because the way we've done it so far, it's defined on compactly supported functions, and we use that property many, many times, right? I mean, it's not even, we can't even make the kernel make sense. You know, that the kernel blows up unless we have a compactly supported function. And the reason it actually makes sense is because of the internal cancellations, which we were which we implicitly used in showing, okay, so let me start again. The kernel a priori makes no sense because it's not integrable, but we have the definition makes sense because we showed that when we have a smooth function and we take the Cauchy transform of the conformal part of the gradient, that turns out to be equal to the Beurling transform. So therefore, the Beurling transform does make sense for compactly supported smooth functions, right? What this identity will allow us to do will be to uniquely define a Beurling transform on any L2 function, which is a priori quite surprising because we really used this smoothness property to make the definition make sense. But we will be able to do that, and I want you guys to not look this up, but just think about this. Why is it the case that being able to do this for every single compactly supported smooth function allows us to define a Beurling transform from L2 to L2, which will have the same property that will preserve the norm? Okay, think about that, and that's where we're going to start from on Friday. All right. Sorry, I overran as usual. Have a great day, people. I will see you all on Friday.